Hi everyone, I am Yuan from Nanjing University, China, and I'm very glad to have the chance to present our work, HoORaYs high-order optimization of radiant distance for recombinant systems. And this is a joint work with Jingwei, Hang, Xianping, and Jian. But actually, all the slides are made by the first author, Jingwei, and he was also supposed to give this talk here, but unfortunately, he cannot get here due to the visa issues. So anyway, I will try my best to make the slides easy to follow. And here's the outline of the talk. First, I will introduce the background and motivation, and then I will describe the proposed approach as well as the experiments. And let's start from motivation and background. Recombinant systems have been widely used in many real applications, and one of the key problems in recombinant systems is the so-called rating prediction problem. That is, predict the ratings from users to items. And in this work, actually, we view the problem as a two-step process. And the first step is rating model design, which actually provides the computation of the predicted rating from, let's say, a user I to an item J. And the second step is optimization task building, which builds an optimization function to learn the parameters from the first step. And let's take matrix factorization, MF, as an example. For the first step, for the rating design, rating model design, the predicted rating from user I to item J can be computed as the inner product between the user's latent profile vector UI and the item's profile vector VJ. And here, UI and VJ are the parameters we aim to learn. And in the second step, MF simply optimizes over each rating Rij, and it actually minimizes the difference between the real ratings and the predict ratings to learn the parameters. Okay, and this slide basically gives a brief review of existing work. And actually, most of the existing work focuses on the first step. That is, they try to, for example, incorporate side information such as the item content, the social relationships between users into the model, into the computation for the predicted rating. And a common practice of the second step is to minimize the difference between real ratings and predict ratings, just as what MF does. So, as we just mentioned, while existing work mainly focuses on the first step, in this work, we focus on the second step. And this slide provides some motivations or explains why we should focus on the second step. This is the basic MF optimization target, and actually we can view it as a self-calibration process. That is, for a given rating Rij, we actually update its corresponding user vectors and item vectors. And here, one problem is that the rating matrix is often very sparse. So as a result, such self-calibration cannot be very accurate. And the solution space for this may be very large. The estimated vectors could be biased. So we are wondering if we can actually borrow the information from the other items and users when we are optimizing a given rating Rij, so that the learned vectors can be more accurate. So this is the basic idea of this work, and the intuition is that the ratings from the same user to different items can reflect the user's rating differences across items. So let's take a look at this example. Here, suppose we have a rating from user I to item J, the rating is Rij. And we also suppose that we have another rating from user I to item J prime, and the rating is Rij prime. So we kind of can define such a distance between these two ratings. We name it as distance 1. And similarly, if we change Rij to R hat Ij, the predicted rating, then we can actually define another distance, we name distance 2, between R hat Ij and Rij prime. And then we can actually define a high order distance between these two distances, between the distance 1 and distance 2. So this is a basic idea that we can borrow the information from other users and items for a given Rij. And the goal of this work is to find more accurate latent profiles. And in particular, we first want to discover a high-order rating distance, and then to make use of the higher-order distance to build a new optimization task to shrink the solution space. Okay, then let's go to the second part. Actually, we have 3 subparts in this part. And let's first go to the optimization model. Here's the basic formulation for MF, right? And then what MF actually does is to optimize or to minimize the difference between the rating Rij and the predict rating R hat Ij, which we call first order distance. And then we introduce another item J prime that the user I has rated, and then we can have this triangle structure where we have the real distance between Rij and Rij prime, and the estimated distance between R hat Ij and Rij prime. And then we define the distance between the 2 distances as the second order distance. Okay, then here's the optimization formulation that we incorporate the second order distance. We have the first order distance, we have the regularization terms, and this 2 actually combines the MF model, and we have the additional second order distance. And as we can see in the previous examples, we mainly focus on the 1 user, 2 items case, right? For a user, we use its ratings from to item J and item J prime. And for this second order distance term, we can actually find that we also use the ratings from other users to item J when we are optimizing over rating Rij. So actually, first order distance considers the same user, same item case, while the second order distance considers the same user 2 items case and the same item 2 users case. Okay, then we give 2 interpretations for this formulation. And the first is geometric interpretation, which helps to explain why the second order distance could reduce the model's solution space. And the second Bayesian interpretation, we actually want to connect the proposed method with existing methods such as probabilistic MF and collaborative topic regression. So the first, a geometric interpretation. Now suppose we have a 2-dimensional space, and we are given the rating Rij and the items vector Vj, and now we can actually have a perfect UI based on, which is actually on the line, on the blue line. And suppose we also allow an error, which is epsilon, and we can actually have the solution space between these 2 red lines. And similarly, if we have another rating Rij prime and a Vj prime, we can actually have 2 more red lines and 1 more blue line, and then the solution space for this case, for this example, is in this diamond area. Okay, then let's see how second order distance works. And now suppose we have in this 2-dimensional space, we have the origin, which is the black point, and based on some transformations, for example, we can assume that the vector Vj is normalized. Then actually the rating Rij can be represented as the distance from the origin to the oblique blue line. And similarly, we can have Rij prime as the distance from the origin to the horizontal blue line. And next is the I hat Ij. I hat Ij can be presented since we actually have 2 worst cases for I hat Ij. We have the error bound, as we showed in the previous slide. So I hat Ij in one of the worst cases is the distance from the origin to the nearest red lines. So this is the short line segment from I hat is the I hat Ij. And then we can have the definitions, the necessary definitions for the second order rating distance. The D, which stands for the distance between Rij and Rij prime, and the D hat, which stands for the distance from hat ij and ij prime. Okay, then we have another worst case of r hat ij, which is the most far away, the distance from the origin to the most far away red lines. Okay, then this is how the second order distance works. We actually can add a constraint that the d hat and d are close to each other, then the solution space can be reduced to a smaller diamond area. Okay, and then the Bayesian interpretation. This is a graphical representation of the proposed model, and we can see that we have actually the previous optimization formulation is based on PMF. We actually add the second order distance on the PMF. And if we further add the LDA part, we can have the second order distance for the CTR model, which combines PMF and LDA. So this is a connection between our method and the proposed and the existing PMF and CTR method. Okay, next, the learning algorithm. So actually, for the optimization target, we have like near quadratic second order pairs. And so the time complexity could be quadratic. And so this is an efficiency issue, and we need to speed up the computations. Here are the two observations. First is that the rating scale is usually very small in recommender systems, for example, 1 to 5 stars. And the second is that the contributions are equal if the rating values from the other users or to the other items are the same. So we actually make use of these two observations. I'm not going to explain the details, but actually we can reduce the time complexity from quadratic to linear. Okay, then let's go to the experiments. And in our experiments, we actually studied the 4 data sets, two for the one-class case and 2 for the multi-class case. The one-class case is that we only have the positive feedback from users. And the multi-class case is a common case where we have, for example, 1 to 5 stars. And then the evaluation setup. For evaluation metrics, we consider recall and AUC for one-class case, and we use IMSC and MAE for the multi-class case. And for the compared methods, we compared with PMF and CTR, since the second order distance are built upon PMF and CTR. And one more thing is that actually the proposed methods actually is very similar to the learning to rank method. So we also compare with the learning to rank method BPR in the one-class case. And to remind this, we define HoORays 0 as the combination of PMF and the second order distance, and HoORays as a combination of CTR and the second order distance. Okay, then this is the result for the multi-class case. And as we can see, the proposed second order distance can help to improve the accuracy compared with their corresponding Bayes method. For example, HoORays 0 is better than PMF, and HoORays is better than CTR. And this is the evaluation result on the one-class case. And also similarly, we can find that HoORays are better than their Bayes and better than the PPH method. So actually, we also have some other experiments considering the efficiency, considering the parameter sensitivity. So you may check the paper if you're interested. So in summary, the experiments show that we can achieve improvement in terms of the recommendation accuracy while we don't introduce too much efficiency burdens. Okay, and finally, conclusions. And in this work, we actually proposed the concept of higher order rating distance, and in particular, we used the second order distance as an example to and build the existing models, build the second order distance upon the existing models. And in experiments, we find that the second order distance can really help to improve the recommendation accuracy while introduce little efficiency burdens. Okay, that's it. Thanks.